Hello there kitties, I'm Kerry, the vacuum tube witch, and today I gotta follow up on the frequency counter restoration that I did after the last video. It's way cleaner inside, and I won't tell you that it works way better, but it's a lot nicer now. Let's get over to the bench. And we've got this frequency counter that you saw before. I did some restoration work. It was a thorough cleanup. First I had to take it all apart, discombobulate it, and clean the parts in the ultrasonic cleaner, and then put it all together, hoping that it would solve the problem with the input circuitry and the wrong readings, but unfortunately it didn't. Worse still, I don't know why this was the case. I replaced every single capacitor in the unit. Also replaced a bunch of diodes and full bridge rectifiers because they heated up a lot. I replaced them with Schottky diodes that limited the voltage drop and power dissipation considerably. So let's take it apart again and see what changes inside. A little modification. I cut down the sides of those plastic inserts. So I can slide the upper and lower panel without having to detach those. I don't know why the manufacturer didn't make them in a way that would provide an easy access to the inside. But as for the inside, look at that! Isn't it a lot nicer than before? Thing of beauty. So all the printed circuit boards have been cleaned. Not just the circuit boards, but all the switches, all the potentiometers. I didn't clean the transformer because the moisture ingress could damage it. So I just left it out. But all the rest, together with the wire harness, look at that! So clean and nice now. Recapped the board. Those are the new diodes, and they indeed heat up way less than before. I didn't take apart the crystal oven for cleaning because it would be a little bit too complex to put it back together, ensuring that the frequency stays as intended. But I took the enclosure apart. All the panels, they went to an ultrasonic cleaner. Unfortunately, I fucked the back panel up because the the markings, some of the markings were just gone, and I had to restore them by hand. Might not be perfect, but it's good enough for Australia. So let's get into the input amplifiers, because those are those as an assembly, that's the single most complex part of the unit. Both parts were cleaned, but unfortunately that killed the trim pots. They just fell apart after I was done cleaning. I had to replace them, so I replaced them with multi-turn trim pots, because I prefer using those for a precise adjustment. And then I also tried to hunt down the bug that caused wrong frequency readings when I connected the counter to a 1 kHz generator, a sine wave one. If I connected it to a square wave, it was all fine. If I connected it to the sine wave generator through my vacuum tube voltmeter, then it also worked fine, but I still had the problem that I couldn't trust the square wave pulse forming circuitry, its accuracy, so I had to do my best to calibrate those potentiometers. The A channel was affected because this one is used for frequency measurement, and I had to set both the feedback control and the diode limiter control bias voltage. I'll show you on the schematic what this is all about. But first, let's get a block diagram to walk you through how the frequency counter even works. So we've got the block diagram in the frequency counter mode. And let's see, starting with the standard frequency generator. The crystal oven generates 5 MHz, and this is doubled, so the internal standard is 10 MHz. And this comes in on one of the contacts, one of the sets of contacts of the frequency range switch. That's no, not the frequency range, but the mode switch. That's this one. So from the mode switch it goes into the frequency divider, and the divider, it's 8 steps of 1/10 frequency, so it comes in at 10 MHz, then we've got 1 MHz, 100 kHz, 10 kHz, etc., etc., all the way to single hertz, and 1/10 of a hertz. That's the 10 seconds period. And the choice is made by the range switch. So if we press this button, it uses the lowest frequency from the divider, and the measurement itself takes 10 seconds of time. So this is pretty sluggish, but accurate for measuring low frequencies. And from the frequency divider and range switch, it comes in on a mode switch again. Gets bridged with the gate control circuitry, both the stop and start control pulses. And this will, together with external or internal tied to 5 volts DC gate control voltage, it will allow the measurement, allow counting the pulses. And where do those pulses come from, you might ask? So we've got the channel A. This is the input amplifier, the insert on the right. It not only amplifies the input waveform, but also forms a train of square pulses, roughly at a 50% duty cycle for the sine wave. Its output comes in on the mode switch, and we can see that this goes to the main gate that is used for counting the pulses with the proper counter. So having the block diagram in the frequency counter mode walked through, let's see the proper schematics of the device. Unfortunately, I had them in separate pages, and those were not scanned perfectly. So I've got all kinds of mismatches between sizes and locations of all the lines. Those two pages, they are slightly accurate. So here we've got the input amplifier, and the pulses come in on the NAND gate here. Then the gate's second input is grounded in the frequency mode. So it will just stay. The output will just stay positive. It will never go. It will never go low. But it also the amplifier also comes into the second gate. This is actually a triple 3-input NAND gate. I see one 74S10. That's a higher speed version of the 7410. And this gate, it also acts on the signal. Let's follow it back to in case of frequency measurement, it will be tied to plus 5 volts, so it will be high. So we've got high or low on the input. Then another signal. And that would go right from the main generator, the standard generator, and because this is an AND gate, and ground. So this is gonna be low. This is an XNOR, or this is a NOR gate, not an XNOR, because an XNOR would have another bar on the input side. So if this is a NOR gate, then if we've got both negative inputs, then the output will be high. Negative, I mean low, not negative. It's not minus, it's 0 volts. So yeah, there's some more circuitry and an AND gate. Yeah. More stuff to figure out. Never mind. Anyway, assume that this gate is active. It lets the amplifier signal through. And what comes next? An AND gate with a JK trigger flip-flop. That, yeah, I think that those flip-flops activate the start and stop logic of the gate control circuit. And yes, this is the LED indicator that lights up when the gate is active. So yeah, that would be it. So when the gate is started and not stopped, this will let the signal through, and this is the input of the counter. And all this, that's the controls for the frequency divider, and also probably also some other circuitry. Haven't really studied this complex circuit. It's a diagram of discombobulation, not as bad as Semtron, but still pretty complex. Superimposing. Can't really superimpose those two because they were scanned at different distances, different magnifications. So if I get this line right, this is already coming apart. So we've got the input, and it comes in on the 125 JK flip-flop. And there's another one. I don't exactly understand how it works, because part of the schematic was already cut off in the original file. But anyway, the pulses from this, they will come in on the first counter. This is a BCD counter, so it outputs the binary digits of the number, like 1, 2, 4, and 8. And they are set to count to 10. This is the latch that accepts the BCD input, and it will store the values, the bits, when it's told to with the memory pulse. It will store them and output them to the Nixie tube driver and decoder, the famous 74141, that accepts the BCD input and outputs 1 of 10 code for controlling a Nixie tube. It has open collector outputs that are capable of withstanding a few tens of volts. So generally that's how the counter works. This one also has a overflow outputs that carries over to the next decade and the next and the next and the next. And the input amplifier. That really was a bitch to troubleshoot, I tell you. And this schematic is a little bit murky. It shows a bit too much overcomplicating things, so I redrew it in my notebook. So okay, let's get back to it. Here it is. So the input signal comes in on a AC or DC switch. In the AC position, it passes through a capacitive coupler separating the DC. In the DC position, this is bypassed. 51 ohms to ensure the 50 ohm impedance. Then it comes in on a voltage divider that wasn't really all that well calculated, because if we wanted to have 1/10 of the input voltage, we'd rather use a 910 kilo ohms to 100 kilo ohms. So the entire resistance would be 1 megohm. And this is paralleled by a small capacitor, a high-pass filter. And then the selector switch, that was the coupling switch, and this is the divider switch. Then another 51 ohm resistor and 100k 33 pico resistor that forms a voltage divider with those two transistors, and the transistors don't transist in this circuit, they just diode, because the base is coupled with a collector, and this diode-tied transistor is a pretty superior to common diodes like 1N3148 or Schottky diodes. It needs to be biased, but I'll talk about it in a moment. So if the input signal, either positive or negative, is too high, this will start conducting and clipping the signal. I wonder if I could make a something like a tube screamer with two transistors instead of diodes. Anyway, after the limiter circuit, it comes in on the field effect transistor. It works as a source follower, high impedance on the input, low impedance on the output, into a regular emitter follower with a bipolar transistor. Those are tied in pairs with a resistor on the positive supply voltage to reduce the common mode noise. And then it comes in on a positive input of a balanced operational amplifier LM733 that has only one output used rather than both, but this is a balanced operational amplifier. It has a differential input and both straight through and inverted phase output. And on the output we've got another follower, lever shifting diode for dropping 2 volts of the voltage on the emitter. Normally we've got something like 3.9 volts DC on the output. So this comes in on a feedback adjustment resistor. And we've got a negative feedback loop. This is a DC feedback. We've got filter caps that form a very good low-pass filter together with the megohm resistor and then another filter stage. We've got a trigger adjustment that goes on only if we use it. That's the spot. It has a switch, and the switch is off when automatic trigger is in action. So this is disconnected, and there's no low impedance, no low resistance in the circuit. It can control the second field effect transistor that works as a source follower, and so on for the negative input. There's no AC on this input, it's just the voltage reference. AC comes in only on the positive input. But there's also another branch here, and this lever controls the bias point of the diode clipper. We've got an adjustment pot here, and by setting it to symmetrical clipping, we adjust the bias of the signal limiter. So I also did that. And back to the output of the amplifier. It comes in on a Schmitt trigger from 2 transistors and a diode. So if the base voltage exceeds a certain level, it will cause this transistor to start conducting, this transistor to stop conducting, and the output will go high. If it drops below the lower threshold, this transistor will stop conducting. The voltage here will go high. Through the Zener diode, it will come in on the base of the second transistor and cause it to conduct, driving the voltage low. And that's how we got the low state. This is another diode tied transistor that clips the output voltage so that it doesn't rise too much above 5 volts positive. Say for 5 volts plus diode drop. And here we've got a emitter follower for the output, and a level shifter that sets the emitter voltage and also collector voltage at a 2K2 to 1K8 point. So that would be something like give or take something like half a volt, and this is the output of the analog section. Comes in to the digital section with 4 NAND gates that this signal drives those gates, but in the frequency measurement mode, they just let it through, because this circuitry is active only in the time measurement mode. The blocking voltage input is normally low, but it's high in the time measurement. So if it's low, and if this is high, then this will be high. This is high. So both highs on a NAND gate, this is low. No matter what the position of the edge switch rising or falling is, we've got negative, we've got low state on this line. Back to this line. So this was low, this was high, right? So this will be high. This is tied to 5 volts DC, so this will be high as well. So this is high. It's always high in the frequency measurement range. This is high. This is low. Hunting high and low. So, if the input signal is high, and this is high, then this will be low, otherwise it will be high. And if input signal is high, and this is low, then this will be high. This is high and this is low. Then this will be high. We established it before that this was high, so in that case it will be low. But if the input signal is low, let's start with this branch. So not high and low. The output is high. And with this branch, not low and low. So this is high. High and low. This is high. I might have jumbled something. Anyway, it's one or the other. It's not both high, because otherwise it's not both high all the time. But yeah, this combination changes as the input waveform changes. And here we've got the square wave output from the front-end unit. Yeah, I probably didn't explain that all too clearly. It happens. So what am I gonna do with this frequency counter, you might ask? Initially I was planning to modify it to extend the frequency range to something like 125 megahertz, so I could use it for tuning the local oscillators in FM radios. But without a way of reliably measuring the input frequency, that might not be the plan that I'm gonna continue with. But I'm gonna put it on my test setup right above the PO25A sine wave generator. They are gonna look very well together. And if you look at the connection, the T connector from the generator's PNC output goes in on the vacuum tube voltmeter's input, and the VTVM has an output that I might just couple with the frequency counter's input, because I used the VTVM for measuring the voltage, but also driving the PFL-34 solid state frequency counter. That it likes a roughly stable output level from the equipment that feeds it. So the vacuum tube voltmeter does a job of setting the measurement range and also the output voltage for any subsequent test equipment. And this is a good thing, because I'll be working with a roughly constant level. So let's get back to the desk. So that would be my new frequency counter. Or clean, or restart. I'm not as happy as I could have been with how the measurement comes out, but it's gonna be a welcome addition to my lab. And I think that on my next video it might already be here. We'll see. And before that happens, you know what? Stay determined and carry on.